Uh, Hello, good morning, one and all. So, in this video lecture, I am going to explain the operating principle of AC voltage controller. So, let me share you the PPT. So, here you can see the presentation for the today's video lecture. So, in the last video, I have explained about the single phase half wave AC voltage controller, both with R load and RL load. Right? So single phase half wave AC voltage controller is also called as unidirectional. So which means with the help of half wave AC voltage controller, either we can control the positive half cycle or we can control the negative half cycle, but not both. So which means to control the positive half cycle, we have seen one thyristor is used, and this negative half cycle is not controlled. So we need to go for uncontrolled device that is called diode. So that is why in case of half wave AC voltage controller, one thyristor and one diode we have used to control only the positive half cycle. Right? Similarly, you can also control the negative half cycle by keeping the thyristor in reverse manner. So now, if I want to control both positive half cycle and negative half cycle, that is called bidirectional AC voltage. And it is also called as single phase full wave AC voltage controller. So we'll see the operating principle for both R load and RL load. So let me move on to the uh, bidirectional AC voltage controller equivalent circuit. Here you can see the equivalent circuit where T1 is used to control the positive half cycle, whereas T2 is used to control the negative half cycle, which means there are two control devices. T1 is responsible for positive half cycle. Similarly, T2 is responsible for negative half cycle. That is why they are connected in anti-parallel to each other, right? So let us see. So this is the power electronics converter, which is converting the fixed AC. So here you can see fixed AC voltage with the fixed frequency to a variable voltage with a constant frequency, right? So to achieve the variation in the output voltage, let us see. Let us consider first with the resistive load. Now here is the AC voltage controller. Normally we'll call it as PEC. This power electronic converter, which is converting the fixed AC to a variable AC voltage across the load, right? So now, as I said, that to this converter, we are providing a fixed AC voltage that you can see here, AC alternating current wave shape, right? So here I can say in one cycle, you can see both positive half cycle and negative half cycle. So positive half cycle is from omega t equals 0 to pi, whereas the negative half cycle is from omega t equals pi to 2 pi. So let us consider the terminals of the transformer are A and B. So if I consider during positive half cycle, so let us consider during positive half cycle, this terminal is a higher potential and this terminal is at lower potential. So if that is the case during positive half cycle, T1 anode is connected to A positive, cathode is connected to B negative through the load. That means T1 will be in forward bias condition. Whereas if you see T2, this is the T2 cathode which is connected to A positive, which is a higher potential. Anode is connected to lower potential, which is B negative. So T2 will be in reverse bias condition and T1 will be in forward bias condition. So that is what you can see here, right? T1 forward bias condition and T2 is in reverse bias condition. So it will goes to off automatically. So during complete positive half cycle, T1 will be in off state. Whereas since T2 it is in off state, whereas T1 it is in forward bias condition, which means we can make it on by applying gate terminal, gate pulse at the gate terminal. So at omega t equal to alpha, firing pulse is given to the forward bias, that's at T1. So from this particular point onwards, the load will be connected to source through T1. So this terminal will be now A and this terminal will be B now. And the current will flow from higher potential to lower potential. So A plus to thyristor T1 anode and cathode to load resistor like this, right? So the current will flow from terminal A to terminal B through the load resistors. So that is why this load will be subjected to source voltage from omega t equal to alpha onwards. So it is following the input voltage, which is a dotted line. And the load is a resistive load. So the load current will be in phase with the load voltage. That means at omega t equal to pi, the net current flowing to the thyristor T1 will be 0. Or the net current flowing to the thyristor T1 may fall below the holding current, which means T1 will goes to off automatically at omega t equal to pi, right? And from omega t equal to alpha to pi, T1 it is in conduction state. So it is replaced with a short circuit and it is carrying the current. And voltage across thyristor T1 will be, ideally it has to be 0 because it is short circuited. But practically there is a 1 to 2 volts voltage across it. So that you can see here. But during alpha, it is blocking the forward voltage. Now, if I want to see the voltage across T2, which is in reverse bias condition. So from omega t equal to 0 to pi, it is in reverse bias condition. And it is blocking a reverse voltage. But from omega t equal to alpha to pi, T1 it is in conduction state, which is connected across T2. So voltage across T1 will be same as the voltage across T2. And that is why you can see 1 to 2 volts, but with negative because they are connected in anti-parallel, right? So this is about positive half cycle. Now we'll move on to the negative half cycle. So during negative half cycle, the polarity will get reversed, right? So now let us see the polarity of terminal A and B. So previously, terminal A is at higher potential. Now it will goes to at lower potential. Whereas terminal B at lower potential, now it will goes to higher potential. So if that is the case, then T1 anode is connected to negative. T1 anode is connected to negative, which is at lower potential. Whereas T1 cathode is connected to at higher potential. T1 will be in reverse bias condition. It will goes to off state. That is what you can see here. It will goes to off automatically. Whereas if I see T2 cathode is connected to A negative, anode is connected to B positive, which means T2 is in forward biased condition. And if I apply the triggering pulse at gate terminal, it will goes to conduction state. So at omega t equal to pi plus alpha. So this is alpha, but with respect to reference point, it will be pi plus alpha. So if I apply triggering pulse to T2 at pi plus alpha, from that particular point onwards, T1 will conduct and it will carry the current. So in which direction it will carry? It will carry the current from higher potential to lower potential, which is from B plus to load resistors to T2 anode and cathode to A minus. So now from this particular point onward, from pi plus alpha onwards, the output voltage will follow the input voltage. And due to resistive load, the output current will be in phase with the output voltage. But at omega t equal to 2 pi, if I see at this particular point, the net current flowing through the thyristor T2 will goes to 0. Or in other words, the current flowing to the T2 may fall below the holding current. So if the net current, that is anode current, falls below the holding current, the thyristor will goes to off automatically. So throughout this AC voltage controller, since the input is AC, a natural commutation technique used to make the thyristor off. So without any additional commutation circuit, the device thyristor will goes to off automatically. That means natural commutation technique are used to make the thyristor off, right? So now I will see the average output voltage and RMS output voltage, which will be extracted from the waveform. So, if I see the area from alpha to pi, this area, if I calculate this area, let us say it is plus 25 volts. If I calculate the area under this positive half cycle. And if I see the negative half cycle, so as I said, the thyristors are triggered symmetrically. So it is T1 is triggered at alpha, T2 is also triggered at alpha, right? So the area under negative half cycle, if I see, this will be the area. And if I calculate the area under this particular curve, let us say it is again a 25 volt with minus sign because it is a negative half cycle. So if I take the average, plus 25 minus 25 divided by 2, that will get 0. So graphically, I can say the average output voltage of AC voltage controller is 0, right? Let us see the mathematically. So now, during positive half cycle, it is V naught average equal to Vm by 2 pi alpha to 2 pi Vm sin omega t d omega t. And this alpha to 2 pi is split into two half cycles. Alpha to pi, you can see Vm sin omega t, integration from pi plus alpha to 2 pi Vm sin omega t. And I can take a Vm as common, Vm, so it is Vm by 2 pi. Integration of sin omega t is equal to minus sin cos omega t. The limits are alpha to pi. And similarly here, integration of sin omega t will be minus cos omega t, and the limits are from pi plus alpha to 2 pi. So substitute the upper limit or lower limit, and you will get 0 minus cos alpha, minus cos phi plus cos alpha minus cos 2 pi plus cos pi minus alpha. This will cancel with this one, and this will cancel with this one. We will get 0. So average output voltage, we are getting 0 even by mathematical analysis. So similarly, we will get average output current is also 0 because average output current will be equal to average output voltage by R, and that you will get it as 0. And even you can see graphically. So see the graphical representation of the output current. So from alpha to pi, we are getting the current wave shape like this. And from pi plus alpha to 2 pi, we are getting the current wave shape like this. So this area will be same as this area, but with negative side, that is why you will get a 0 average output current. Let us see the RMS output voltage. So again, we'll derive the RMS output voltage from the waveform which we have drawn just now, right? So if you recall the waveform, and alpha to pi, we are getting the positive half cycle, and from pi plus alpha to 2 pi, we are getting negative half cycle, right? So which means both the half cycle are symmetrical. So now I can take only one half cycle. So root means square for the one half cycle. So root and the mean is 1 by 2 pi, 1 by pi, alpha to pi, Vm square sin square omega t d omega t. So now sin square omega t is equal to, you can write it 1 minus cos omega t by 2, and the limits are alpha to 2 pi, alpha to pi. And I can take Vm out of the root, it is Vm by under root pi. And if I separate and if I integrate, and I can substitute the upper limit or lower limit, you will get the RMS output voltage as Vm by under root 2 pi under root pi minus alpha plus 1 by 2 sin 2 alpha. Similarly, I can calculate the RMS output current. So RMS output current will be equal to V naught RMS divided by R, since the load is resistive load. So it is Vm by R root 2 pi under root pi minus alpha plus 1 by 2 sin 2 alpha is the RMS output current. So this is about R load, and now we'll go for RL load. So now we are changing the load with the RL load. So before going to see with the RL load, let us see. So as I said that average output voltage will be always 0 if I trigger the thyristors symmetrically. If the thyristors are not triggered symmetrically, we won't get the average output voltage as 0. So this is the case only when the thyristors are triggered symmetrically. And we can vary the RMS output voltage from 0 to a maximum of Vm by under root 2 pi. Right? When alpha equal to 0, it will be Vm by under root 2. When alpha equal to pi, we will get 0. So by varying the alpha from 0 to maximum of pi, we'll get the RMS output voltage Vm by root 2 to 0. Right? So let us now we will move on to the RL load. Just we are replacing the load with resistive inductive load. Now here you can see the resistor and inductor, they are connected in series, right? And the operating principle will be same. As I said in the last slide that during positive half cycle, T1 will be in forward bias condition, right? T1 will be in forward bias condition and it will start conducting from omega t equal to alpha onwards. Whereas T2 will be in reverse bias condition, it will goes to off state automatically. And when I see during negative half cycle, negative half cycle, so reverse will happen. So T1 will be in reverse bias condition, so it will goes to off state. Whereas T2 will be in forward bias condition, and from pi plus alpha onwards, it will be start conducting, right? So this is about the operating principle of thyristor T1 and T2 during positive half cycle and negative half cycle. Now, as I said, since T1 will be in forward bias condition from 0 to pi, so I can apply triggering pulse to T1 at omega t equal to alpha. Alpha is a firing angle. T1 is triggered. So from this particular point onwards, the output voltage following the input voltage. We don't know up to what extent it will follow, and that depends upon the value of inductor. So now, since in the previous case, the load is resistive load, that is why the current and the voltage, they are in phase. Now, the load is inductive and resistive combination. And due to this inductor, the current will lag the voltage by angle phi, and phi is given by omega equal tan inverse omega L by R. So depending upon the value of omega L and R, there is a lag in the current with respect to voltage. That is why you can see the current is lagging the voltage and it is charging the inductor during positive half cycle, which is from alpha to pi. Thereafter, the inductor is discharging, right? So the both charging and discharging is taking place through T1. So T1 will be in conduction state till this particular point. And here this point is called beta. Now beta is the extinction angle, and at omega t equal to beta, you can say the current flowing to the load is extinguishes to 0, or the current is discharging to a 0 value. So which means beta is defined as the angle measured from the reference point. Here it is a reference point at which you can say omega t equals 0, the point at which the current extinguishes to 0. That is what beta, right? And from alpha to beta, T1 will be in conduction state. So voltage across the T1 will be 1 to 2 volts. But during alpha, it is blocking the forward voltage, right? And voltage across the T2 is also 1 to 2 volts, but with negative polarity, because T1 and T2, they are connected in anti-parallel. So it is minus 1 to 2 volts, right? And again, during negative half cycle, as I said, which is from alpha omega t equal to pi to 2 pi, during this period, T2 will be in a forward bias condition, right? And I can apply triggering pulse to the forward bias thyristor T2. At pi plus alpha, T2 is triggered, and it is carrying the current. So during negative half cycle, this will be at lower potential, this terminal will be at higher potential. The current will flow through higher potential, through load to T2 and back to the lower potential. The current reversal is taking place. That is why from pi plus alpha to 2 pi or beyond 2 pi, the output voltage will follow the input voltage. And due to presence of inductor in the load, there is a lag in the current. Thereafter, it will charge, and then after 2 pi, it will discharge, right? And the discharging portion depends upon the value of inductor, because energy stored in the inductor is given by half Li square. So if the value of inductor is large, the inductor will store large amount of energy and it will take more time to discharge. So instead of discharging here, it may discharge here or even it may discharge here, right? So that depends upon the value of inductor. So I took the value of inductor is low, that is why it is discharging just after omega t equal to 2 pi. So till this particular point, the output voltage will follow the input voltage. That is why you are getting the negative peak here and here, right? So which means from pi plus alpha to pi plus beta, T1, T2 is blocking the voltage, forward voltage, sorry, T2 it is in conduction state. The voltage across T2 will be 1 to 2 volts. And the same voltage you can see across T1 because T1 and T2 they are connected in anti-parallel, but the voltage across T1 will be with negative value because of anti-parallel connection. So now after seeing the waveform, we can easily able to derive the expression for average and RMS output voltage. Now if I see the average output voltage, so now if I see here, so this negative area will cancel with this positive area because both are voltages, and this positive half cycle will cancel with this negative half cycle. So graphically I can say the average output voltage equals 0. Let us see mathematically. So to see the mathematical expression for average output voltage, so alpha to 1 by 2 pi, it is the time required to complete one cycle, one input cycle. So 1 by 2 pi, you can see this positive half cycle, which is from alpha to beta. So the integration is from alpha to beta Vm sin omega t d omega t. Again, a negative half cycle will be from pi plus alpha to pi plus beta. So the integration is from pi plus alpha to pi plus beta. Again, it is Vm sin omega t. So I can take Vm common, Vm by 2 pi. Integration of sin omega t will be minus cos omega t. Here also it is minus cos omega t. And by substituting the upper limit and lower limit, you will get the average output voltage equal to 0. Even you can see the average output current also 0 because if there is no voltage, there is no current. That is why V naught average divided by Z, that will give the 0 voltage, 0 current. So now with this, from this waveform, we will see the RMS output voltage expression. So to see the RMS output voltage expression, we will consider only one half cycle, which is from alpha to beta. So which is of pi duration. So root mean, which is 1 by 2 pi square Vm square sin square omega t d omega t. But we are getting the waveform from alpha to beta. So that is why the integration is from alpha to beta. So I can take Vm out of the root, square root will get cancelled, it is Vm by under root pi. And sin square omega t I can write 1 minus cos 2 omega t by 2. So and now I can separate it, I can integrate it, and I can substitute the upper limit and lower limit. So if I substitute this one, I will get the RMS output voltage as Vm by under root 2 pi under root pi minus alpha plus 1 by 2 sin 2 alpha minus sin 2 beta, where beta is the extinction angle, alpha is the firing angle, right? And similarly, you can calculate the RMS output current, which is RMS output voltage by Z. So this is the expression for RMS output current. So now with this expression, we'll try to solve one problem on it, right? So let us consider this problem. Now it is a single phase AC voltage controller, feeds power to a resistive load of 20 ohm. Input voltage to 230 volts 50 Hz. We need to calculate the RMS output voltage, load power, input power factor, average and RMS currents of thyristor at firing angle of 45. So alpha he has given 45 degrees, load is a resistive load, input voltage is 230 into root 2 will give the V maximum, because V naught RMS is Vm by under root 2 pi under root pi minus alpha plus 1 by 2 sin 2 alpha. So alpha he has given 45, and Vm is 230 into root 2, and this is pi minus alpha, which is 180 minus 30 degrees, 45 degrees. So which is in degrees. We need to convert this degrees into radians. That is why it is multiplied with pi by 180, and that will give the RMS output voltage as 219.30 volts. So if I know the average RMS output voltage, that divided by resistance will give the RMS output current. And you can easily calculate load power, which is V naught RMS into I naught RMS. So V naught RMS is this much. That multiplied by I naught RMS, that will give a current of around two, power of 2404 watts. Similar input power factor, which is V naught RMS divided by Vs. So now V naught RMS expression, we know this expression. So Vm is under root 2 times V supply. So V supply will get cancelled. This is the final expression. And if I substitute alpha here, which is 45 degrees, and I need to convert this degrees into radians, which means here I need to multiply with pi by 180. That you will get it as the input power factor is 0.9547. So this is about AC voltage controller, that is fully AC voltage controller, and we have seen one problem here. Thank you. I will stop here. In the next video lecture, we will see the other converter. Thank you.